Hi guys, so this is example 36 on our section of uniform circular motion. It's on page 28 of your textbook. Question 1 says you observe a car traveling to the right at 20 meters per second. Calculate the angular velocity of one of its tires, which has a radius of 0.30 meters. Okay, so we first need to ask what we have. So that 20 meters per second, seeing that it's in meters per second, that is our linear velocity. So we've got a linear velocity of 20.0 meters per second. Then we are given a radius of 300 meters. So the radius, not 300 meters, 0.300 meters. That would have been a very big tire. In any case, and they ask, calculate the angular velocity. So we want to know omega. So our relationship between angular velocity and linear velocity is given by the equation V equals omega times r. So omega is our angular velocity. That's what we want to know. Our radius is 0.300 and our linear velocity is 20,0. Both has 3 significant figures, and therefore it would be appropriate to have our angular velocity as 3 significant figures. So dividing 20.0 by 0.300, we get an answer of 66,6 repetitive radians per second. So this answer to the appropriate number of significant figures, therefore, will be 66,7 radians per second. Okay. Example 2, they say consider a clock, assuming it's not a ticking clock, but one whose hands move uniformly. Determine the angular velocity of the second hand of the clock. Now, that's quite important. The second hand of the clock, according to me, I hope I'm correct, is the hand that indicates the seconds. So in other words, we now have to ask ourselves, but what can we do? How can we solve this problem? Well, how long does it take for the second hand of the clock? The second hand, it's not like the second hand, it's the one that measures seconds. So in other words, it takes 60 seconds to complete a full revolution. And the time for a full revolution, we define as period. So that time is equal to 60 seconds. Okay. And a full revolution means that our angular displacement in this case, which is indicated by delta theta, will be 2 pi. Because remember, a full revolution, yes, it's 360 degrees, but in terms of radians, it is 2 pi. So in terms of our angular velocity then, our angular velocity is our rate of change of angular position. So that is our formula that we have for that one. In this specific case, it is the one full revolution of 2 pi divided by the full time, which is the period of 60 seconds. And calculating that, we get quite a small value. We get a value of 0,10. And then there are other numbers as well, but I'm just going to limit it to 2 significant figures here. So it's radians per second for angular velocity. Now, question B says that find the speed of the tip of the second hand. Now, that would be our tangential speed if the hand is 18,0 centimeters long. Now, once again, the relationship to our linear speed and our linear velocity and our angular velocity is this relationship indicated by this formula. Now, in this case, and this is where it becomes quite tedious doing calculations with significant figures. In the previous one, I rounded to 2 decimals over there. However, this was a division calculation, and I'm going to do a multiplication calculation here. So it's only appropriate that I do not use the rounded value in my second problem, but the value over there of 2 pi 60. So my angular velocity for this problem, I'm also going to put it in as 2 pi over 60. And my radius now is 18 centimeters, 18,0. Okay, so calculating this, I get a value of 0,018. Now let's quickly talk about this value, guys. It's in meters per second. It's a speed. It's a scalar, so I don't need to include any direction. Okay, so here I had 3 significant figures. They are only indicated to because there's quite a lot of uncertainty as well if this clock is accurate. Can I say it's 60.0 seconds? This clock is however limited because there will be an uncertainty in that second value over there. So that's why just indicating 60 is fine, and then I'm limited to 2 significant figures by that 60 seconds. So in other words, my answer over here will also only have 2 significant figures. Then problem 3. In problem 3, they say the Earth makes a complete rotation around the Sun once every 365.25 days. Now, let's talk about that 365.25 days. Now, once again, this then is our, yes, you're correct, it can only be our period. Yes, because it's the time for one full revolution. However, it is now in days, so remember, we will need to convert it. And then they say the Earth has a radius of 6.4 times 10 to the 6 meters. The first question, question A, says, what is the Earth's angular velocity? Now, once again, in this case, we can say, well, yes, we know our angular displacement. Our angular displacement for a full revolution will be equal to 2 pi. And then our period in this case, they said, was 365.25 days. But we know we need the period in seconds, so we will convert it to seconds by multiplying by 24 because there's 24 hours in a day. And in each hour, there's 3,600 seconds. Okay, now I'm not going to calculate the value over here because remember, in AP Physics, we work with significant figures. And therefore, I don't want to use the rounded value over here. So now, my angular velocity, I can say, will be my change in angular position divided by the time it takes for that to happen. So my change in angular position, we already said, will be 2 pi divided by my time, and now my time is the 365.25 days times 24 times 3,600. Okay, now in terms of this, you might ask, okay, which of these figures limits you? Now guys, there should be exactly 3,600 seconds in an hour. There should be exactly 24 hours in a day. And a year contains 365.25 days. So all of these are constant values. So in terms of this, this one has 5 significant figures. And that one will be my limiting one because all of these have infinite significance. So in other words, it would be appropriate here to say, okay, I'm going to round to a value that has 5 significant figures. And this angular velocity then becomes 1,9910 times 10 to the 7 radians per second. Okay, and then they're asking question B, what is the instantaneous speed of a point on the Earth's surface at the equator? So in this case, we want the linear speed. So our relationship between linear velocity and angular velocity is given by the angular velocity times the radius. So the angular velocity, and once again, you won't use the rounded value here. You can use the value on your calculator even, because all of those actually had infinite significance. So I would use that value, okay, and then it's times the radius, which only has 2 significant figures, because yes, although it's a constant, you can get more accurate reports of the radius of the Earth. So using that that value that I was given to 2 significant figures, I get that the 2 significant figures for the instantaneous speed at the equator would be 1.3 meters per second. Okay guys, I hope these examples help and that you enjoyed this lesson. Thank you.